All right, section 8.2, the Bohr theory of the atom. This is going to be kind of quick because of the fact that, well, everything after this is kind of the development of this, by contrast, very simple view of an atom. Okay, so interaction of light and matter. When gaseous atoms of a given element are heated, they emit very specific wavelengths of light. This is called an emission spectrum. The different colors in fireworks are emissions from specific elements with energy provided by explosive chemical reactions. A unique emission spectrum for each element is inconsistent with the Rutherford model of the atom. And if you remember the Rutherford model of the atom, that was this idea that, well, you've got the nucleus in the center, and then electrons are kind of all over the place. But they're all over the place in these very simple models. Okay, so there's one and these rings. So electrons freely circled the atom's nucleus. Niels Bohr, this guy right here, proposed the Bohr model. It's a pretty clever name that he came up with. So he won the Nobel Prize for it in 1922. The idea is that electrons must be found at only specific distances from the nucleus in orbits. Okay, so the Rutherford model was nucleus. I need to develop what I said just on the previous slide, was that an electron here, and I'm trying to draw these and consider these distances. These first two electrons are different distances from that nucleus. The Bohr model was they have specific distances. Okay, electrons travel in a circular path in what are known as discrete energy levels. Each element has a unique set of different energy metals. Now, what's important to know is, despite him winning the Nobel Prize for this in 1922, this is not NOT. We italicized it and I've underlined it, not the current model of the atom. But this was very important work which was used to develop the more contemporary and current model for an atom. Electrons do not actually travel in circular orbits. We'll get to that in the next section 8.3, but we'll proceed. How the Bohr model explains absorption and emission spectra. The lowest energy level closest to the nucleus is called the ground state. Okay? An absorption spectrum is observed when electrons absorb energy and move to higher energy levels known as excited states. Electrons in excited states will emit energy to return to the more stable ground state. Okay, so they absorb energy. So like this level is where they are the ground state. They absorb energy coming in, and so they'll elevate. And then as they kind of go back to their regular state, that's when they emit energy. Electrons in excited states will emit energy to return to the more stable ground state. The light emitted is the emission spectrum. The energy of the light absorbed or emitted exactly matches differences between the existing energy levels. Okay, so as an example, here's the emission spectra for hydrogen, helium, and neon. So these excitations, or these different energy levels that they can ultimately topple back from, you see all these different colors. Now, if you look at hydrogen, helium, neon, well, think about those atoms. They are different in terms of their subatomic particles. Now, the Rydberg equation was developed to explain the energy associated with that. The Rydberg equation is as follows. 1 over lambda, the wavelength of light, is equal to this, what's known as the Rydberg constant, 1.097 times 10 to the 7th inverse meters, times the 1 over n squared sub 1 minus 1 over n squared sub 2. Now, wavelength, lambda is the wavelength in meters, and n1 and n2 are positive integers. The Rydberg equation combined with E equals hc over lambda allows for the calculation of the energy difference between specific energy levels. Now these N1 and N2, those are the different energy levels. So for instance, energy level 1 and energy level 2. Now, we're not going to do any calculations associated with this, or we're not going to do a specific calculation. I just wanted you guys to be familiar with where that's coming from and what the role of the Rydberg equation is. And here is kind of a manipulation of it, where you can see the energy associated with movement between energy levels. Okay, so one aspect of the Rydberg equation to be familiar with is that it works only for the hydrogen atom, which has a single electron. With that said, however, all atoms emit characteristic spectra, which can be used to identify them and have unique electronic levels. So it doesn't fit perfectly to the Rydberg equation if it's not a spectra for hydrogen, but all different elements or all atoms are going to emit a characteristic spectra. So electronic energy levels. The biggest difference, or the biggest energy difference in any atom's energy levels, is always between the first and second energy levels. The energy levels get closer together the farther from the nucleus that they are. So that would be like, here's our nucleus, and here's energy level 1, here's energy level 2. I'm not really drawing that well. I'd like you to focus only on the top half of this. Energy level 3, 4. I'm trying to draw them closer together, successively closer and closer together. An electron removed from its atom is assigned an energy level of infinity and an energy value of, well, 0 joules. The lower energy levels are given a negative value, as they must have less energy than an electron in the highest energy level, infinity. Now, here's a representation of those different energy levels. So the difference between energy level 1 and 2 versus 3, and the distance between 1 and 2 and 2 and 3 and 3 and 4 and everything like that, these energy associated with these different energy levels, they are decreasing ever so slightly. So negative 2.42 times 10 to the 19th up to negative 1.36. So the energy associated with that has basically been cut in half, and then it gets even less than being cut in half here, and so on. All right, well, like I said, we're not doing any calculations associated with this, but I do want you to know the function of the energy, or the Rydberg equation. It gives you a means to calculate the energy associated with movement of electrons between different energy levels.